Welcome to the new course that we will all be experiencing in this semester. It's called Linear Systems and Signal Processing. Let's start the class. So this course, basically the name of this course is Signals and Systems, okay? The official name is Linear Systems and Signal Processing, but it is Signals and Systems. So this name of the textbook also is Signals and Systems. So what is Signals and Systems? In science and engineering, what we do is that we try to understand the nature. We try to understand what's happening in nature, how things work. And after we understand that, for that to become science, we try to model it using mathematics. So we try to find a formula, a way to model what's going on in nature in a mathematical term, okay? So in this effort, why do we do that? So that we can classify different problems under different groups, such as we call them linear systems, linear time invariant systems, periodic signals, random signals, etc. All of these, what they mean, of course, we talk about in details. So we talk about mathematical models of the physical world around us. After we model them, we try to use these models to design a system. It could be an electrical system, electronic system, telecommunication system, a mechanical system. It could be an aeroplane, or it could be a bomb, or whatever, okay? So we use our understanding and the mathematical model of our understanding of physics of things, and we develop things. This we call engineering, right? To use the physical principles and to develop a technology or a product is called engineering. As electrical engineering is what we do. We develop intelligent systems, electronic systems that do a certain job in a nice manner to increase the quality of life, comfort, or productivity, or whatever. So in this sense, modeling the physical systems, we make a distinction. We classify, and we say that there are signals and there are systems. Okay. So we say that the physical things around us, we look at them in a fundamental manner, and we say that some things we call them signals, and the other things we call them systems. So signal, what is a signal, for example? Signal is just, in mathematical terms, it's a dependent variable. Like, I can talk about, I can put here a thermometer, assume this is a thermometer, I put it here, and let's say this has a digital display, and I just keep looking at it and see what is the temperature, how does the temperature change, okay? So the reading of the temperature, it says, let's say I'm also heating it from here. Somehow I'm blowing air into it, hot air into it. I will see that the temperature at this point, for every second, will increase or decrease depending on how much energy I pump into it. So that thing that you would say that, so this is the time I start, and I would say this, so I can just observe or measure a dependent variable based on time, okay? This is time, and this is some physical quantity. Of course, it doesn't even have to be physical quantity, right? But I will give you an example like that as well. So this is one thing. So temperature as a function of time, for example, is a signal, okay? How about the water level in Omerli Dam, right? And the reservoir. So every day, the municipality measures it. Says that, okay, water level is today is 51 meter and 20 centimeter, okay? So in summer, when there are less rain than usage, then you start seeing, okay, the water level became now 49 meter, 48 meter, 47.73, whatever. So you can look at, again, this is again time. This is water level. So you would see that this is, first time I measured it, it was after 1 day. So day 1, it is day 2, it is this, okay, etc. So here, what do you see? This is of course, let's call this temperature, okay? Temperature. So we are measuring the temperature at every moment, right? And here, we are measuring the water level in Omerli Dam. Every day, let's say, every day, 3:55 p.m., okay? Periodically. After 24 hours, we go and have a look at it and record it, okay? So this is called, again, this is a signal, right? But it looks different from this. What is the difference? This is called discrete time, okay? So what it is that we are just taking samples of the level. Of course, the level, water level in Omerli Dam always exists, isn't it? Even if you check it, you measure it or not, there is always a level. And that level would change millimeter and nanometer level. It would change all the time. It will go up and down. But we are just measuring it once a day. So we are doing this in a discrete time manner. So this is continuous time, okay? Meaning this is discrete time. Meaning, as an engineer, we say that instead of just measuring the data every second, every nanosecond, I don't need to, it's not going to change too much anyway. So I can just check it once a day, okay? Why do we do this? Because computers work in a discrete time. Our computers, they have something called clock, right? So we could talk about clock speed. What it does is that at the clock speed rate, it will do one more operation, okay? So between one clock cycle and the other, nothing happens. So at every clock cycle, it's going to do something. So inherently, digital computers work in discrete time. So therefore, we measure things in discrete time manner. Okay. How about, so here you get to think that things always change with time. It's not necessarily true. Let's talk about this classroom, okay? We can talk about, we can just have 100 thermometer, okay, heat sensors we call them. We call these measurement devices in engineering language, they are called sensors, okay? You could have level sensor, you can have temperature sensor, you can have pressure sensor, you can have altitude sensor, you can have millions of different kinds of sensors to measure things. So we can just place, let's say, 100 thermometer or heat sensors in this room. So we can talk about how the temperature changes on X and Y, right? So you talk about, then you have X, okay, and Y. So you can just okay, so you have at these points, let's say, you have sensors. Okay? This is the room. In 3 dimensions, so you can talk about changing of temperature on a plane depending on the coordinate, right? So how would we picture this? We would say that this is X, Y, and this is temperature. Right? So you would say again, so at this point you measure and you will have different height. Okay? You would say this much, that much, etc. You would have a different, it's difficult to plot in 3 dimensions. So you would have your independent variables are X and Y, and your dependent variable is the temperature you read at that coordinate, right? When we talk about how about in this volume, I can just X, Y, Z, I can just fill this room with temperature sensors, one here, one here, one here, and one here. And so in X, Y, and Z, I can have 1,000 sensors. Then I have to plot something 4-dimensional in that case, right? Which I cannot plot. So I can talk about 3 independent variables, X, Y, Z, and temperature as the dependent variable. Or I can talk about a picture. In an image, you can just take a photograph, okay? So let's say you have a tree here, okay? This is a picture of a tree, okay? You have some cloud here, etc. And I cannot make good pictures. So you can talk about pixels. All of you know about pixels, right? In the computer and graphics, you have that. So you divide this into 600 to 400 something. Each one of these is called a pixel. Then you talk about this X, and this is Y. And let's say this is just a grayscale image. Then you talk about what is the level of gray here. It can be between total black to total white, right? So you have different levels there. So you can talk about what is the grayscale of each of these pixels. So then you have a 2-dimensional signal here. In temperature's case, you have 2 or 3-dimensional signal. And in this case, the independent variable is not time. Okay? So in temperature, it was time. In level, it was time. Here it was space, but I could also bring in how does this change with time, right? So the temperature could be changing also by time. Somebody might be blowing into some hot air here. Okay, you could have some window there open. So how does the temperature change in every point in this space? Okay, so it is again, it could be 4 independent variables and 1 signal. What is that? The temperature in the room. The change of temperature in the room with space and time, for example. Is it clear what is a signal? Are we in the same wavelength? Okay, good. Or stock market. It doesn't have to be always a physical quantity. So it could be stock market. Istanbul stock market, let's say, they talk about now stock market opened at 9:30 in the morning, okay? So it opens, it was 101, something like that. I never believe in the stock markets, by the way, okay? Then it went up a little bit. There are some good news, and then better news, it went up, and suddenly whereas the bad news came down, right? Just does this kind of crazy things. It's not a physical quantity. It is what is the value of how much buying and selling is being done, and how much, what is the value of that index. That index is calculated in a sophisticated manner depending on what is being bought and sold, and what was the price, and what was the offering, etc. Okay? So this is again time, and this is index, stock market index. Okay? So it is not temperature or gray level, it is just stock market level. So you could talk about, let's say, you have meteorological station, and you could have many measuring stations for weather predictions that you could just talk about the wind and the temperature and the humidity and many other things, okay? All of these are signals, okay? So what is a system? The system is this room, okay? So where the system is the other part of the physical world. So you have the signals. Signals are inputs or outputs of variables, some things you measure. Systems are the structures. Systems are the place or the machine or the physical environment that are subject to signals, and they give out response to those kind of signals, okay? So we have, so signals and systems are separated in these manners. Systems are structural things. They are built, or they are like components getting together. Or if it is an environmental system, it is like Istanbul has this kind of, it has Bosphorus and the Marmara and Black Sea and whatever. It has this mountain and the 7 hills, etc. And this affects how the weather behaves here, or what is the air quality, or how often it rains, etc. In Rize, my hometown, it rains all the time. Why? Because the system there is such that it just has mountains and this and that, and it will force the clouds to rain down on Rize, right? So it can be a natural system that is not man-made, or it can be a physical system that as engineers we do, okay? We build it, we put it together. So I'm just telling you this, or stock market is a system, right? Stock market itself is a system. You have a mechanism there, you have a structure where the companies are part of it and they buy and sell, and so there is a mechanism, there are laws that define it. So you have bylaws and the laws and the companies there and the certain structure that everybody knows, and that, according to that, people invest in there, which is an input, and the stock market index changes accordingly, or the profit you make could be another signal coming out of this. The level of profit each person makes also could be considered as, so it is, I'm just trying to make it as vague as possible so you don't think that system is just an electrical box. It is, universe is a system, okay, the entire universe with sun and the moon and all what you see on the sky and the earth is a part of that system, and signals are just the variables, the light coming out of it, or the light going out of it, or the temperature of it, or the distance from one to another. All these things that we measure and we attribute a value to, they are also called systems. So it is, signals and systems are very, very wide concepts, okay? Of course, as engineers, we cannot do much with such a general things. So what do we do? As I explained before in my previous classes, what we try to do is that we start from the simplest possible system. Okay, we say, okay, let's start from what is the simplest system you can have. Okay, this is it. Okay, what is the other system? So how can I convert the other more complicated system into a combination of these simple systems and try to find what that system does based on my previous knowledge for this simpler system. Or for signals, we do the same thing. We say, okay, how can I analyze this system? Okay, I say that, okay, there is a signal called a sinusoid, a periodic signal, and it's a very nice signal. I know how to analyze it and everything. Okay, how can I look into other signals? Can I consider them as a collection of these simple signals? Okay, the answer is yes. And we call them frequency analysis. So that's a very big discovery that we can analyze systems and linear time invariant systems on a spectrum basis, meaning we just take very special signal called the sinusoid and design our system for that simple signal, and then we call that a certain frequency. And we talk about frequency range. Our system will behave this way in this frequency range. It will behave that way in that frequency range. What we mean is that we have a collection of many, many different sinusoids. So it's always like that. You try to simplify. And this simplification is possible only because of modeling. So we have to have models to understand the physical world. And we have to have models for signals. And we have to have models for systems. And start from the simplest to more complicated and try to understand the entire thing. Any questions? Okay. Let me give you at this point an example. An example of a system and a signal. Let's say I have an electrical circuit. Okay, it has a power source called V. Okay? So I have R1, R2, okay? So I have a voltage source here. Okay, this is a system where I am able to change this any way I want. Okay? And I am measuring this. This is my output. I call this output. I'd like to know what is the mathematical model that connects, okay, my input to output. Okay? So why is this an output? Who decides that this is an output? It's me, right? Whatever you want to measure in your system, for example, who decided that I will measure temperature here, right? So I can say that this is what I'm interested in this circuit. Why? Because I'm going to connect something else here. I would like to know what is the voltage here. When I apply a certain voltage here, what would be the voltage here compared to this one? Okay? So that I will connect it to another system. And that system will do something else, and output of that will be connected to another system. And maybe I will have thousands of systems interconnected like that. So in electronics, when you see that huge electronic system that has billions of components, you don't build it all at once. This is how it is done. You have basic building blocks of it, okay? And you have the specifications, input and output. This will be the voltage level. This is how much current you can pump into this, and this is how much voltage you can get out of this, and this is how much current this can supply you. So you stage by stage, you design from simple, basic building blocks, you design your very, very sophisticated, complicated looking system. Okay, so it starts from basic building blocks. So it's not necessarily that you start from the scratch and you just have design everything all at once. Okay? So let's talk about this one. Of course, this is very simple to analyze, isn't it? Just there is one loop here. You call this loop current I. Okay? And so this is, you just always make these references. Did you take circuits course, the first circuits course? Okay, good. So you know this very well. So this is, you just write the loop equation here is minus V plus VR1 plus VR2 is equal to 0, right? You make loop around, so the total has to be 0. So therefore, you just write this VR1 and VR2 using the Ohm's law. So minus V plus R1I plus R2I is equal to 0. That means R1 plus R2I is equal to V. So I is equal to V over R1 plus R2. So what is Y? Y is VR2. So what is that? That is R2 times I, right? So R2 times I. So that is R2 over R1 plus R2 times V. Okay. We call this, so what is this telling you? So this output, so when you have an input voltage, okay, this is, so VT, okay, this is YT. When you have an input voltage, VT, whatever it is, okay, no matter how it changes by time, the output voltage you will have here is just determine R2 divided by R1 plus R2. For example, if R1 and R2 were equal, you say if this is 10 volt, this will be 5 volts, right? Any question about this? Please ask. Let me see who is going to ask the first question in this classroom, other than when is the exam, okay, about the technical material. So I look forward to the first question. Okay, so this is very simple system. So what is a signal here, and what is a system? Let's just try to understand this. So what is a signal? Can you somebody tell me a signal here? Huh? What is a signal? Input voltage. This is an input signal. So you are inputting something here. You have control over this. So it's a signal, okay? So you pump into something here. You connect a battery, or you can just connect your wall plug here, okay? So you have an input, and what is another signal? It is my output signal, isn't it? So what is the system? The system is this interconnection of these elements, how they are connected, not only what they are, but how they are connected. So their structure, how they are connected and what is connected and everything, that is a system. So this structure is your system. And the signal, of course, I could also say this is also a signal. The value of the current at this point or the voltage at this point is also a signal. Or at this point, of course, it's 0, but whatever, okay? So you can talk about any point, the voltage at any point or current at any point as a signal. Of course, you could do something else as well. You could talk about that. What would be the temperature here? When I apply this voltage here and that here, you could also measure the temperature. How much heat does it dissipate, right? What would be the temperature of this? This is also very important. So you could talk about that as well. Or if this is an LED diode, then you talk about how much light does it emit, right? You could talk about intensity of the light. You could talk about color of the light. So signal is a very, very general thing, and we make use of that in engineering a lot. And of course, electronics engineering, we're proud to do that, right? We are proud to be electronics engineer because we make the world run around us. So you are very lucky to be electronics engineer. Okay, so this is, of course, this is a very, very simple system. What do we call this? This is a proportional system. So the output, Y, is just constant. It's a proportional to the input. Okay? So you can just, given the input, you just multiply the number, you get the output. So this is a memoryless system. I will tell you about what is memoryless system. This is not a dynamical system. It's a static system. Okay? And everything. So to make to make you understand the difference between the simplest one and the next simplest one, let me give you another example. Okay? The other example is you just have one capacitor and one resistor. Okay? Of course, we are covering the first chapter of the book today. So today will be the first chapter. We will finish the first chapter. Okay? Of course, I am not following the examples. I am giving my own examples and my own explanations. But there is a material that you can read there. Okay. So let's talk about. Okay. You have again a voltage source, and you have a capacitor and resistor. Okay? So how do we analyze this? Same way, right? So there is one loop here. You call this loop current I. Okay? So you talk about, you just write this. So it's in opposite direction. It's minus V plus VC plus VR is equal to 0. Okay? So then you have IC is equal to what? C dVC dt. So this is the equation. And what is VR? VR is equal to R times IR. Of course, IR. Here, there is only one current. Let's say they are all equal. So it is I is equal to IC, and that's also equal to IR. Right? So then you have here VC minus V plus VC plus R I is equal to 0. So I is equal to minus V plus VC plus R times C dVC dt is equal to 0. In other words, we just write it in a nice form. dVC dt is equal to V minus VC. Okay? Just let's divide this. So dVC dt is equal to minus 1 over RC VC and plus 1 over RC and V. So this is called, what do you call this voltage of a capacitor from circuit theory there's? Huh? The course you took in circuits. What do you call it? State variable. And what is another state variable? Current of the inductor. Very good. Okay? So when you have, unless you have a degenerate case, like have two capacitors connected in parallel or in series, or two inductors connected in parallel or in series, number of state variables you have for a current is equal to number of capacitors plus number of inductors, right? So that's very good. So since we have one capacitor here, we are not surprised that we will need to have a differential equation to be able to understand what this is. Okay, so here we have this example where you have no capacitor, just input and two resistors. An input-output relationship was just proportional. But in this case, so let's say this is my also output. Okay, This is y. So y is equal to VR. Okay? So what is VR? VR is equal to, so y is equal to VR, and that's equal to, from here, V minus VC, right? So that's it. So input and output are related like this, and VC is determined by this differential equation. So, and of course here, you know, this is V, so you are going this way, so you have this much, you drop this from this, right? And the remaining is, you are not surprised, it's V minus V. VC is applied here, okay? So in the standard form, so this is what you are going to have, okay? So how do you solve this? So how do I really find out who took differential equation course? Okay, even if you didn't, if you took, all of you took matrix linear algebra. Who did not take linear algebra? Is there anybody who did not take linear algebra here? So everybody took it, right? So in linear algebra, we taught you this, how to solve system of linear differential equations. We taught that, right? So this is just, so how do you solve this? This is just V is equal to e to the minus. Of course, I will talk about this. We will learn these things in detail, in very nice and systematic manner, how we solve these things. But I just want you to see 1 over RC VC 0 plus from 0 to t e to the minus 1 over RC tau V t minus tau d tau. Okay, so this is t here. T minus t over RC. Tau is, this is called convolution. Again, we will teach you that. Okay? So this is the kind of relationship you have, okay, with VC is related to the input like this. It's a dynamic system. So the things happen, for the things to happen, some dynamics get into picture, right? Some differential equation, some dynamic structure. It behaves according to a differential equation. So it is not like this. It's not like this tahteravali, you know. You just pull this side, the other side goes up. It's not like that. There's some memory. It has its own dynamics. Maybe you push it like this, it will first go down, then it will come up, right? So it is much more sophisticated behavior than this proportional behavior, okay? Any question on this? There is probably 1 over RC here, okay? 1 over RC. Okay. So let me just take this here so that I have room for the other example. And I will write the other one without solving it, okay? Okay. So Okay. So I'd like to have, again, this is my input. And let's say this is my output. So this is equal to VR2 is my output. I'd like to know how does my output change with respect to the input. Okay? So again, you will write two loop equations. You know these things very well, okay? So you will write your Kirchhoff's laws and loop equations here. And what you will obtain after 5-10 minutes or 15 minutes is that so we have two state variables, isn't it? Okay? These are all variables in terms of t. So this is how the input is affecting the state variables. Okay? And what is the output? Output is just y is equal to VR2. So that's equal to voltage in this, right? So you would just consider this loop here. So you would have V, right? This V minus VC1, one state variable, minus VC2, isn't it? So you have, again, so in a matrix form, this is how we would write this. Minus 1, minus 1, VC1, VC2, plus V. Okay? So in general, in systems, you would have x dot is equal to AX plus BU, y is equal to CX plus DU. This is like linear time invariant systems are in this form. So in this case, D is 1 and this is etc. Okay, you have one output. Of course, I could say I have two outputs. Let's say I can also talk about this is my Y2. So what is Y2? Let me write that one as well. So this is Y1. Y2 would be, who would tell me that? What is the voltage here? VR2. What is this voltage here? It's V minus VC1, right? So in other words, you would have minus 1, 0, right? VC1, VC2, plus V. So you can just put this together as well, and you have Y1, Y2 is equal to minus 1, minus 1, minus 1, 0, VC1, VC2, plus 1, 1, and Y. So this would be 1, 1, and V, not phi. This would be, so in block diagram, so you have V and you have Y, right? This is when we are only concerned about one output, this voltage here, we can call it one input and one output system, okay? So it is V and Y. So when you talk about one input and two output systems, then you have y1 and y2. So it becomes a more general case, okay? So we have all these. One of them would be called single input, single output system. The other one would be called multivariable system, okay? So all of these, during your studies in this department and afterwards when you go for master's and PhD, you will learn more and more and more of these, and you will change the world accordingly. Let's give it a break for 10 minutes so we can do the second portion of our course for today. Okay, let's continue. I didn't tell you the solution of this, but instead of telling you the solution of this one, for those of you who did not learn how to solve linear system of differential equations before, let me tell you about that in just one sentence. Okay, when you have, let's say, x dot, okay, vector, a matrix, times x, plus b, u, okay, these are or functions of time, okay? How do you solve this? The solution of this is as follows, and we will learn this in this course, but because we talked about this example here, let me just give you the solution without proving it, because in a few weeks' time we will go through it in detail. But just since you are supposed to know this from your linear algebra course, let me just write it here. Okay, so this is xt is equal to e to the at times x0 plus integral from 0 to t e to the a tau b u okay, this is what it is. So as you see, it depends on the initial conditions. What are the initial charges stored in your capacitor? Capacitor is, of course, a device or an element that stores energy, right? So it is a storage, energy storage. As a matter of fact, there are some batteries that people are trying to develop, next generation batteries based on capacitor or supercapacitors. Okay, how can we use batteries as a means of, how can we use capacitors as a means of batteries? That's a current active research topic or technology topic. Okay. Okay. So this is, so far we talked about what is system, what is signal, and what did we say again? As engineers and scientists, we try to model the physical world around us, right? The nature. For us to be able to do something, we have to write it on a paper, right? We have to put it on a paper. So whatever the wind or water level, etc., for us to be able to do something on it, we have to be able to model it so that we can write it on a paper. So we do things on the paper and the computer, and we develop something, and we go and plug it into the physical world, okay? And this is called system design, engineering design. Okay, so signals and systems is the way we classify the physical world around us. The things that goes on around us, we call some of the things, we call them signals. Some of the things, we call them systems. And these are all interrelated, meaning a system wouldn't mean anything if it doesn't have some signals related to it, meaning a system gives out something, some output. That's a signal. A system is affected by some inputs, which is a signal, okay? So therefore, signals and systems are interconnected, and they are a part of one big universe around us, the physical world around us. So they are strongly related things. Why do we call some of them signals, some of the systems? Because we need to have a systematic way of looking at things. Okay? So we have to simplify the understanding of the nature. We have to come up with simple models, building blocks of this nature, and just one by one put them on top of another and come up with a sophisticated system, or to try to understand the very complex world around us and make use of it. Okay. Now we start talking about the classification of what are these things. Okay? Power. So as electrical engineers, when we have a resistor, right? Okay, R. So we have V and I. Okay? What is the power of this that is spent on this resistor? What is the power? How do we define it? Who's going to tell me that? Power. I know the current and I know the voltage. What is the power? What? IV, yes. So power is V times I. Okay? Okay? Of course, since it's a resistor, I can write this as, I can just say V is equal to Ri. Okay, this is V, and I have I, so this is Ri squared. Or I can say that I is V over R. So this is equal to 1 over R V squared. Okay? So in terms of resistor, this is what power means. So we generalize this. Okay? In general, we say that when you have a signal xt, okay, a signal xt, okay, has power absolute value t squared. Okay? So we call this the power of the signal. Okay? So what is the energy? So this is PT. So energy of a signal is for interval t between T1 and T2, how much energy we consume on this resistor, right? So we know how much it's heated. Or maybe we want it to heat, maybe we are using it as a heater to heat our room, right? So sometimes heat is not always something bad. Sometimes it is desirable. By design, you want your resistor to give out heat so that you don't freeze. So how do I define energy now? What would be the energy? It's integral from T1 to T2 PT dt, right? In other words, X. So this is the energy of your signal in a given interval. How much energy it is giving out, okay? Or how much energy it is carrying in an interval. So power has to do what? Power has to do with a time, right? At a time. So for example, I am not very powerful. Now I have no power, right? So power has to do with that instant. So power is something instantaneous. But energy is how much effort or how much power you gave out for every moment, infinitesimal dt time, right? This dt. So you collect all the power you had for every infinitesimal time and you add them up. That's what integral is. And that will give you the total amount of power you spend in a range. We call that energy. We can also talk about what? We can talk about average power, right? What is average power? What would be the average power? What would that be? So let's call it P average. That would be 1 over T2 minus T1 from T1 to T2 xt square dt. So you just divide the total energy to the length of the time interval. That gives you, on the average, how much power you had or you applied, or how much power you spent, whatever you want to call it. In the first part of this course, I'm not going to do it like book. I will mostly talk about continuous time systems. Okay? I gave you examples of discrete time systems, a couple of them. But I will first talk about continuous time systems. Okay? In the second part of the course, after some weeks, maybe after a month or something, we will start talking about discrete time systems. And it is equally beautiful, and it's not any more complicated. But I don't want to mix them, okay? And that's how the course was designed, and I agree with it. So the first half of the course will be about continuous time systems, and second half will be about discrete time systems. The mathematics involved is slightly different. Okay. Okay, how about the total energy of a signal? So let's say, energy, total energy of a signal, total energy. So you have a signal xt, right? We say that in an interval, it was in an interval, you have E is equal to okay. Now, if you take the case, okay, let's call it ET from minus t to plus t xt square dt, and take limit t go to infinity et, which is limit t go to infinity minus t to plus t xt square dt, okay? We call this the total energy of a signal, okay? So you are given a signal, and you would like to know what is total energy of that, okay? So in other words, to write this is from minus infinity to plus infinity. Let me give you an example of these things, okay? Let's talk about, let's say my xt is something like this, okay? It is 0 for all negative t's, and it is 1, and then it is between 0 and 1, it is 1, and it becomes 0, and then 0 again. Okay, if this is my xt. What is the power of this signal? Well, let me make this 2 so that we see the difference. Okay, 2. What is the power of xt? So power, pt, is what? It is xt squared, right? Let's plot it. Since this is by plot, the easiest thing is to plot the power as well. This is xt. This is t. So what will this be? 4 and 1 and 0. So this is the power. This is pt. As a matter of fact, let me change this a little bit. Okay? And let me make this -1 here. So to make the, so what will be pt here then? Okay? This is, so pt becomes this. So square of this signal, isn't it? So we take square of it to get the power. Okay? What is the energy? So what is, let's call this E infinity. What is E infinity for this signal? What is it? Integral of this, right? What is that? Area. Good. So the area has two components. One is this, and the other one is this. So integral, that's equal to the integral. So this is 4 and 1. So it is 4 plus this is so it is 5 joule or whatever, energy quantity. Okay? So that's the energy of it. So why is energy important? This is extremely important to classify the signals. Okay? So we talk about bounded energy signal. In physical world, can we have a signal that has infinite energy? Can you have such a thing? You can have things with infinite energy, right? Like not infinite, very large energy. You could have, for example, sun has extremely large amount of energy. That's feeding us with energy for the last 5.6 billion years. It's just giving out all that heat and light and everything. Right? It never runs out, thanks God, right? If it didn't run out, we would all die. So it's huge, but is it infinite? It's not infinite. It is still a finite amount of energy that is there. And it is giving it out in some very nice manner called fusion. Okay? So we talk about, we say that all physical signals in the nature, they have finite amount of energy. Meaning, for all physical signals, for all physical signals have finite energy. Okay? All physical signals. So there's no physical signal that has finite, infinite energy. Therefore, all physical systems give out signals with finite energy. If they try to do otherwise, what happens? What happens to those systems? They are destroyed. They just burn themselves trying to do something impossible. So we call those kind of systems unstable systems. Okay? So stability and instability is this. So it would burn down. Okay? They would be destroyed. So after a while, when they try to give, for example, very large voltage output, very large current output, that system itself would burn. Or if it's a mechanical system, it would be destroyed. Okay? If it is anything else, it would just break down. Okay? So when you have a system, we talk about system. Okay? This could be anything. Okay? Just a system. It has an input, and it has an output. So mathematically, let's call this xt, and let's call this yt. So this system, somehow, okay, I don't know how, okay, it's just taking an input, doing something with that, and generating an output. So we say that a system is stable if for every bounded input it gives out a bounded output. This is the most general definition of stability for a system. If the input is bounded, but should be correct for understand signals and what we can do them. So let's have a deeper understanding about signals now. Okay. Signals. Some operations, signals operations, let's say. Let's say I have a signal I have such a signal, okay? This is called xt. Okay, I would like to plot some, let's say, zt, and zt is x t minus 3. So I make a change of variable, xt minus 3. Okay, how would the plot of this, how could I plot this? I give you this one. I'd like to plot zt. Zt is just, we replace t by t minus 3. What does this mean? For what's happening at t equal to 0 will happen here when t is equal to what? T is equal to, this is 3. 3. So whatever is happening here for t equal to 0, here you would say that this argument here should be 0, right? So you would say, okay, this is shifted. Okay, so here at 0 it was 2, therefore this argument, when is it? So this is at 3. Okay? And then when this argument is 1, then t is equal to 4, isn't it? I didn't do a good plot here. So I will just change this. Okay, this is 1. Okay. This is 4. Okay? So this is called time shift. Okay, this is time shift. Shift, time shift. So when you put here any t0, so the plot is shifted in the right direction. It is, if it is minus something, shifted in the positive direction, t0 amount. Okay, it's just shifted. Meaning, I do something today, and I do the same thing tomorrow. It will be the same plot tomorrow, right? This is shifted. Okay. Okay, if I have, let's say, this is xt, same thing. Okay. And here I have zt. T. Okay. So for t equal to 0, so what is the plot of this? T equal to 0 at t equal to 0, this is the same as, zt is the same as xt, right? So it is 2. Okay? When the argument is 1, This is still 2. When the argument is 1, then it becomes 0. So when for this to be 1, what should be t? Huh? So I'm just looking for this, right? So well, for what t you have this change here? 1 over 2. Yes. So this is 1/2. Okay? So this is called what? This is called time shift. This is time scaling. Right? Time scaling. This is like doing fast forward, isn't it? So this is like you are watching a movie in normal speed, and you are just here watching it in double speed. So this is like playing it in fast forward mode twice. Or if I were to do another plot, let me do it here. If I were to have how would that be? Then in this case it would be, this is 2, right? This is 1, and this is 2. Okay? So this would be in slow motion, right? So I would just slow it down, stretch the time out, right? So we do all these things. These are, of course, very simple, elementary topics. Okay? So time reversal. So you have t, let's say, okay, 2. This is xt. And you have zt is equal to x minus t. Okay? So x equal to 0. So when the argument is 0, both of them are 0, right? So they meet here. Good. So when t is equal to 1, this is x minus 1. What is x minus 1? What is the value of x minus 1? It is 0, right? Here it is. This is this is what it means. In this plot, I just show it wherever it is non-zero. This means everywhere else it is 0, right? That's what it means. So, as a matter of fact, I should have done, let me just cut down from here. So, whatever happens at t equal to 5, for what t it will happen for zt? For what value of t you will have this value of xt? Minus 5, yes. Okay? So this is time reversal, okay? It's like playing backwards, right? So you score the goal like they do that in soccer games. You score a goal and they make it run backwards. In Kemal Sunal movie also, they sometimes did that in the past. You must have seen that. So you just play the video backwards, okay? So this is time reversal. Okay. Let's talk about periodic signals. So these were true for any signals, right? Some basic operations. You can talk about many other operations. We will do that when time comes up, okay? So let's talk about now special signals, periodic signal. So periodic signal is this. X t is equal to x t plus t for all t. This means for all t. Okay? Such a signal, if there is such a capital T, such a signal is called a periodic signal. Okay? So this is means for all t. That's what it means, this terminology. So let me explain it here so that we can use it. Such a signal is called periodic. Called a periodic signal. And T is called period. Okay? So this is a periodic signal T. Any T satisfying this called a period, right? But the smallest such T is called the fundamental period of x of t. So this is in general. So of course, can someone tell me a periodic signal? Sine t, right? So we all know it very well. So you have t so this is 0 pi over 2 pi 3 pi over 2 etc. This is 2 pi. So this sine t, this is t and sine t. This is periodic. Why? When you look at the value here, it is the same here, okay? It is the same here, and it's just same here, right? The value here is repeated here and here. It's just every value after interval of 2 pi, it's exactly repeated, right? So it's called a periodic signal. Another one, can you tell me another one? Cosine t, right? So cosine t, let me plot it here. It is, okay? So again, 0 and 2 pi, okay? It repeats this cosine t. Others, tangent, right? Cotangent. And 1 over sine x, 1 over cosine x. These are all periodic. But they have, some of them has weird plots, right? Going to infinity, plus infinity, coming back from minus infinity, and all those things. Of course, it doesn't have to be sine and cosine. What else? Let's have other periodic signals. One of the most famous one is this square wave, right? So let's say this is 1, this is minus 1, okay, this is, let's say, 2, 3, 4, 5, etc., 6. Okay. So this, I'm not a good picture maker, I'm sorry. I wish I was. Okay. 6, 5, etc. So this is also a periodic signal. What is the period here? Length of the period t. What is t here? T is 4. Right? Understand better, it's not only sine t. So let's talk about in a bit more details. Then I will tell you something big. Now, let's talk about sine omega t. Okay? Let's plot this one. Omega is just a fixed number. Okay? So for t equal to 0, it is 0. When is this 1? So let's talk about 1. Okay, when does it take this value? So it should be omega t1, let's say, should be equal to what? Huh? Pi over 2, right? So when t1 is equal to pi over 2 omega, so pi over 2 omega, this becomes 1, okay? Then when is this 0 here? Omega, let's call it t2. What is that? That should be equal to pi. So t2 is equal to pi over omega, right? Are you following? Right? When is it minus 1 here? So let's call this t3. So omega t3 should be equal to 3 pi over 2, right? So t3 is equal to 3 pi over 2 omega. So 3 pi over 2 omega. And when it is 0 again, omega t4 is equal to 2 pi. Right? So t4 is equal to 2 pi over omega. Right? T4. 2 pi over omega. And this will just repeat like that. So, what is the period here? Fundamental period T0 is equal to what? 2 pi over omega, right? So for sine t, period is 2 pi. For sine omega t, it is 2 pi over omega, okay? And this omega is called the frequency. The frequency, circular frequency of the sinusoid, okay? How about sine omega t plus phi? Okay, let's plot this one. Okay. Let's for easiness, let me take an example. Let me just take phi is equal to pi over 4, okay, so we don't get confused, okay? So what is the value of xt for t equal to 0? It is, for t equal to 0, it is sine pi over 4, isn't it? So which is 1 over square root of 2, okay? So for what value this is going to be pi over 2? So I ask for, so it's going to be something like this, okay? So what is this T1? So omega T1 plus pi over 4 is equal to, what should this be? Pi over 2, isn't it? So omega T1 is equal to pi over 2 minus pi over 4. T1 is equal to pi over 2 omega minus. As a matter of fact, let me leave out this omega for the time being, okay? We can always scale it, okay? So this T1 is equal to this one. So this is pi over 4, right? So this is 2 pi over 4, so it is pi over 4. Okay, so it is shifted towards left like this. So it is, when you have a phase, you just, it's like time shifting. You are shifting your sinusoid back and forth, okay? It's called a phase. Of course, you can look at cosine as a 90-degree phase shift of sine, right? Or vice versa. So this is a time shift. So in general, we talk about a sinusoid like this. Of course, this would include also cosine, isn't it? By picking this phase change appropriately, you can just, this means also the cosine omega t, depending on what you take the phi. Any question on this? Come on, there should be some questions. Who is going to ask question? Is it that simple? Is it? Excuse me? This one I took, for simplicity, I took omega equal to 1, okay? So like the most basic sinusoid. Just so that here, what I'm showing is the time shift this brings in, right? So in the view of omega, you will just have here omega and omega. It's just, so here, we already talked about the frequency there. Here, I just want to show you the effect of the time shift, the phase. Phase is time shift. Is everybody following? Good. Here is the important thing. The question we ask is the following. Sine omega t plus phi is a periodic signal, okay? And we know how to play with this very well, okay? But there are other periodic signals other than sine omega t, right? We had that square wave, and just you can think of zillions of different kinds of periodic signals. The question is, can I represent any periodic signal in terms of sine t with different frequencies? Okay? Can we do that? Huh? All the time, not some of the time. I mean, yeah, theoretically some of the time, meaning it should be finite energy and there are some Parseval's conditions and things like this. But any periodic signal can be written in terms of combination of sines and cosines, okay? And this is called Fourier analysis of the signal. Fourier series exactly does this. We will tell you in a very simple manner in the coming weeks how to do that, okay? It's a very intelligent way of looking at things. How to analyze any periodic signal and consider all of them, they are sines and cosines. This very basic approach and way of looking at signals made entire telecommunication science possible, okay? This is how we have telecommunication systems. Meaning we consider signals as any signal as linear combination of infinitely many sinusoidal signals. Combining them together, each one has different frequency and different phase. So how can we combine infinitely many different frequencies, put them together and modulate them and combine them, subtract them, multiply them, whatever, do anything you want with them. But the basic thing is to analyze them into their frequencies and look at the signals in terms of these basic building blocks, which are the sinusoids. These made entire telecommunication industry possible. So it is very, very important. Okay. But I'm not going to talk about that today. Just want to make the connection, because when we talk about periodic signal, we should know that. Okay? So expect that in the coming week. So you will learn very beautiful things here in this course. This is really one of the most beautiful, maybe probably the most beautiful engineering course you will ever have. Because this really brings out the most basic and simplest principles, definitions, and methodologies of electrical engineering. As a matter of fact, engineering. All of them are extremely simple, and they are very well understood, very systematic, and they mean a lot on what you can do, and they make you understand what is electrical engineering, as a matter of what is engineering. So therefore, expect this. So we talk about even signals. This is very simple. It says that x minus t is equal to xt. So whatever you have here, okay, so this what it's saying is that whatever you have here for t should be equal to what you have for minus t. Okay? This is called even signal. What is an odd signal? The odd signal is x of t is equal to minus x minus t. Okay? So this is let's say you have something like this, okay? Whatever you have here for t, you go to minus t, okay? What you should have here is should be negative of this. This is like you put a mirror here. This is a mirror, right? 45 degrees. It is just reflection of this one. Here the mirror is just vertical, okay? So you have two mirrors here, okay? So this is an odd signal. This is an even signal. So can we say that every signal is either even or odd? Can you say that? No, of course not, right? But we can say the following. Every signal can be written as an addition of an odd signal and even signal. That is general. It's very simple. You can say that, okay, you have x of t. You can write it as xt plus x minus t over 2 plus xt minus x minus t over 2. Let's look at this one now. Okay, let's call this x1. So x1 is xt plus x minus t over 2. Is this even? This is x1t. What is x1 minus t? What is it? It's x minus t, isn't it? Then this is x minus minus t, right? So it is xt divided. So can I say that this is equal to x1 of t? So this signal is an even signal, right? How about this one? So let's call this x2t is equal to xt minus x minus t divided by 2. So what is x2 minus t? What is this? xt, x minus t, right? Minus xt divided by 2. So can I write that, just take minus out, then you have, and take this here, xt minus x minus t divided by 2. So can I say that this is minus x2 t? So therefore, this is odd, and this is even for any xt, isn't it? I have no condition on xt. But is this equal to xt? Of course. This and that cancels. So therefore, any signal can be written in terms of a symmetric signal and anti-symmetric signal, or even signal and odd signal. In matrices also we have a similar thing. Okay, just to tell you that. A matrix is called symmetric if A transpose is equal to A, right? But being symmetric is a very special case. Can I write every matrix in terms of a symmetric matrix and anti-symmetric matrix? Yes, I can. This is how I do that. I can say A is equal to A plus A transpose over 2 plus A minus A transpose over 2. Is this equal to A? Because these A transposes cancel, right? And A over 2 becomes A. So what is this symmetric? If you take transpose of this, A plus A transpose, is it symmetric? Take transpose of this. So transpose of, when you add two matrices, please everybody listen. Everybody listen. When you add two matrices, A plus B transpose, what was this equal to? This is equal to A transpose plus B transpose, right? When you take transpose of this, this is A transpose plus A transpose transpose. What is A transpose transpose? It's A. So this is symmetric. How about this? This is A transpose. When we take transpose of this is A transpose. This is A over 2. So this matrix that if called B. So B transpose is equal to minus B. Right? So same thing. In matrices and a signal, you have the similar thing. The importance of this is as follows. When you have this quadratic form, quadratic forms are defined for symmetric matrices. As a matter of fact, in complex case for Hermitian matrices. But if A is not symmetric or Hermitian, what does this mean? This means exactly that. So this is, please prove this. This is the same as A plus A transpose over 2. Okay, this is equal to that. As you see now, this is symmetric. Okay? So the other part does not have any contribution to the quadratic form. Okay? So this for any matrix, for any real matrix. If it is complex, what do we make? We would make this star. So transpose and conjugate, right? So it becomes Hermitian of that matrix. So it is a similar thing you have for signals, okay? Isn't this very nice? This is just that this anti-symmetric part does not have any contribution to your quadratic form. Just take symmetric part of it. Okay, another very, very important basic signal that we use, this is our building blocks, simple building blocks, is we talked about periodic, now we talk about exponential functions. So we talk about x of t is equal to c e to the at. Okay? So for t equal to 0, it is c, assuming c is positive. Okay? and it will either go like this, or it will either go like this, okay? This is for A negative. This is for A positive. Okay? These are called exponential functions. You will see that linear time invariant systems, their responses will have exponentials like this, and sinusoids, and combination of sinusoids and exponentials together. So everything will be like this, and the step functions. Okay? So when A is positive, does this have, is it a bounded energy signal? Can you have this in nature? No. But you can have it until you realize that you are going nowhere, right? So you see that it is exploding, so you say that, okay, shut it down, otherwise it will burn my system, okay? It's going out of hand. Okay, so it's not a bounded energy signal, okay? So unit step function is function t. It is 0 when t is negative. It is 1 when t is positive. Okay? So this is ut. This is called the unit step function. So it is 0. So this is like you turn on your battery. Tuck, you turn it on. Of course, in practice, what will happen is that it's going to be something like this, okay? So nothing happens instantaneous in nature, okay? And this is practical. This could be very, very small time, but nothing goes from here to there immediately. Why? Then derivative is infinite, so you cannot have infinite derivative, right? Derivative means energy, so you don't have that much of energy, okay? Okay. So you can talk about, for example, u t minus t0. What would that mean? This would mean shifting it, right? So this would mean shifted unit step function. Okay, you talk about now impulse function. So impulse function is the derivative of this, okay? So it is 0 everywhere, and it is this at the origin. This is called Dirac delta function, as a matter of fact, impulse function. So the way we define this is not with this value. We say that minus infinity to plus infinity delta t dt is equal to 1. As a matter of fact, this is the same as minus epsilon to plus epsilon delta t is equal dt is equal to 1. Okay? A good approximation of this, it's not exactly this, but the way to understand this is that we say, okay, so we take a signal like this. It's magnitude is 1 over epsilon, and width is epsilon. Okay? So integral is equal to 1. What is the integral? The integral is just the area under this curve. So it is epsilon times 1 over epsilon. So the area is to 1. So integral from, let's say, minus epsilon to plus epsilon. Let's call this other delta t, okay, delta epsilon t, or let's call it delta epsilon t, okay? So this is equal to 1. So when you take epsilon go to 0, it will always, for any epsilon, this area will be always 1, right? So when you take epsilon go to 0, so when limit epsilon go to 0, delta epsilon t is called delta t. And it's a function that is not defined by its value. It's defined by this property. Okay? So this is alarming. Nobody's asking questions. Either you understand everything, but some of you are looking at their telephones, so I don't think they are understanding anything. Or you are not understanding, you understand nothing, so you are afraid to not to ask. So which one is it? Do you understand? Did you understand everything I told you today? Okay? Please, when you are in classroom, I require that everybody turn off his telephone, okay? Bringing his telephone to the classroom is allowed, but turn it off. If I see anybody looking at their phone, I will point and I will say, please turn off your phone from now on. Okay, I didn't warn you before, now I warn you, for your good. Okay, shifted. So, shifted impulse function is delta t minus t0. Okay? How is this? So you just take the same thing. Okay, this is t0, so you have it here. So integral, okay, this is t minus t0. Okay, this is very interesting. This is also, we call it a sampling function. Okay, what it does is, it will sample your function, isn't it? Let's have a look at this. So Dirac delta function is very important. Let's say I have a function f of t, right? Any f of t. And I multiply this, I have my Dirac delta function, let's say, at t0, I multiply this with Dirac delta function. So I have Dirac delta function t minus t0, okay, and f of t, and dt. Okay, I take integral of this, minus infinity to plus infinity. Okay, I can approximately say the following. This is from t0 minus epsilon to t0 plus epsilon, delta epsilon t f t dt, t minus t0, I'm sorry. Okay? Can I say this? For very small t, approximate. That's what this means approximate, right? So what am I saying is that instead of this, I take the following, like t0 plus epsilon, and this is 1 over epsilon. So I multiply with this. What will be the result here? I wish I drew it here, but I will just do it here. Okay? The result will be t0 plus epsilon, and it's going to be something like this. Right? Everything else is 0. Okay, and what is this going to be? This, if this was, let's say, ft0, and this was ft0 plus epsilon, right? So this is going to be f 1 over epsilon, 1 over epsilon, right? What is the integral of this? So what is this area when epsilon goes to 0? Okay? So this is just, I'm multiplying with, where is that? Did I erase it? No, here it is. I'm multiplying it with a square like this, right? So when I take this equal to 0, what is this going to be? This is going to be f t0. This will go to ft0. In other words, this is equal to ft0. Okay? So multiplying with Dirac delta function and taking the integral is just taking the sample of the function at the delayed thing, okay? Delayed point. Any questions? So let's say you have a system. So system 1, it has an input, it has an output. Okay, you have another system, system 2. It has an input and output. Okay, we talk about interconnection of these systems. Let's say if you take system 1, I will call it S1, okay, S1, S2. With U1 and Y1, and I have S2, U2, and Y2. So if I make the output of the first system as the input of the second system, okay, this is called serial interconnection. Okay, so this is a new system, right? This is a new integrated system. Input of the first system is the input of the new interconnected system, and output of the second system is the output of the new interconnected system. So this is called serial interconnection. Of course, we can talk about also parallel interconnection. So you have U1, you have U2, you have Y1, you have Y2. So if you combine the inputs, you can just talk about these two systems. You just combine their inputs and you add their outputs, okay? Let's say you just, okay, add their outputs and you have a new output that is addition of the two inputs, okay? You can also have a combination of these two together. So you can have S1, S2, okay, S3, for example, okay? So you can think of many other forms. So then we talk about, so output of one system becomes input of the other system, etc. Okay? Then we talk about feedback system. It's very, very important, feedback. How much time do I have left? Feedback systems. Okay? In this case, what it is that you have a system, S1, let's say. This has an input, this has an output, okay? Then you take this output, okay, and you take another system and you feed it back, and you say that don't enter it like this. You feed it back here and subtract from the input. And the input to your system becomes a combination of your input that you want to do something with, and the signal you measure and do something with it, possibly something what we call controller, pass it through a controller, do something such that this system, overall system, behaves the way you want, okay? So let me tell you a few general things about this. In electronics engineering, electrical engineering, and in many engineering disciplines, for example, in signal processing, a filter design, we design our own system, okay? We write down our specifications, and we say that I would like to design a filter that has this and this and this band pass characteristics, and this and this and this stop characteristic, okay? So which frequencies to pass and which frequencies not to pass, okay? So we, starting from the specifications, we use design techniques and we come up with our system. So we start from, we can design any system we want using different methodologies, okay? Using passive elements only or using transistors and many other techniques. In control systems, on the other hand, the system you are given a system, okay? It is either a system, a machinery designed by somebody else or aircraft or something, and they have certain aims to do that. They ask you as an electronics engineer to please design an electronic system for this so that it can do a better job, okay? It can track a target and shoot it, or it can fly very smoothly an aeroplane, even if there's too much wind outside, okay? You will never feel it inside, so that it stabilizes all of those without you feeling it. It will just it will measure what is the wind and everything else, and it will take corrective action so that the passengers in the plane, they can just drink their water and just go on their business with much hurdle. So in control system engineering, this system is given to you. So this is a physical system that is given to you. You are stuck with it. The only thing you have is you are able to select the input you enter into this, and you are able to measure the outputs, okay? So for what input, what kind of output it generates. You have access to this input and output information. And you are asked to design a control system that will modify that such that together with the control system and the physical system, they together will behave the way you want. That's control engineering. So in designing a filter or electronic system, you start from scratch and you build it as you want. In control engineering, you are stuck with something and you want to modify it with adding another external system, what we call controller, to it to make it behave the way you want. Any questions? Okay. What are the things? What are other things we have? Just let me mention this. You have memoryless system. Memoryless system, meaning system without memory, okay? What are these? Let's say you have a system. You have U and Y. So YT is equal to sine 5 UT. Okay? So the output does not depend on any past value. What happened in the past is not important for this system. What is important is, what is it now? This is just living the moment, okay? What happened yesterday, what kind of input there was, nothing. Just what is there today is important, right? But if you remember the example we did in the beginning of the class, so we had a V, right? And we had a capacitor and the resistor. And this, we call this VC, okay? Then what was important, VC turned out to be that dVC dt was minus 1 over RC VC plus 1 over RC V, right? And this we called Y, so Y was equal to minus, it was V minus VC, right? This is equal to, as you see here, the solution of this was VC t was equal to e to the minus t over RC VC 0 plus some integral 1 over RC 0 to t e to the minus tau over RC V t minus tau d tau. So the output depends on the initial conditions, right? So what was the, how much charge did you have in your capacitor in the beginning? That affects your current state, okay? So this is called a system with memory. It's a dynamical system, right? System with memory is a dynamical system. It remembers the past, okay? So such a system is system without memory, okay? This just output just depends on the input at that time. Okay, time varying system and time invariant system. What is time invariant system? Can you tell me? What do you think from the name? What makes you think of it? A system that will have the same response for the same input. It doesn't matter when it is applied to, right? For example, if this system, if I apply a sinusoid to it, the response I will get today, applying the same input, will be the same output that I will get tomorrow. I will get the same output, isn't it? What will be the difference? It will be time shifted. So this means if you shift the time of the input, system is the same system, the response will be the same as the output you got, just shifted in time, same amount. That's what it is, right? For example, so if I have a system S, this is U and this is Y. Y is equal to 2U, let's say, okay? Yt is equal to 2ut. Okay? If I apply u t minus t0, so this is what? Whatever happens here for t equal to 0 will happen here when t is equal to t0. So it is delayed, right? So let's call this u1. And corresponding output, let's call it y1. Okay? So that we don't get confused. So what will that be? So y1t is equal to 2u1t, isn't it? So this is if input is u1, then output is y1. So what is u1? 2 u t minus t0. But what is this? Isn't this just put here, instead of t, just put isn't it the same thing? It's just shifting the output, right? In this one, if you just put ut minus t0 here, you get the same thing, right? So to see the difference, that is not always the same thing. So let me take the same system, a different system. Let's call it S1. This is y, and this is u. And y is equal to t, 2 ut. Okay? To see the difference, how is this time invariant or time varying? Time varying, right? Yes. Okay. So what I want is this: if ut gives you yt, ut minus t0 should give you yt minus t0. It should be just shifted in time. It shouldn't be. Okay? So if you want, so in this case, so when ut you have, of course, gives you yt is equal to 2t ut, right? When u1 is equal to ut minus t0, what is the output? So this is u1t. u1t is equal to ut minus t0. So what is this? What is the output for this? y1t is equal to 2t ut minus t0. Okay? Is this the same as, is this equal to y t minus t0? Is this equal to that? What is this? It is 2t minus t0 ut minus t0, right? Are these equal? No, right? This is 2t, this is 2t minus t0. So they are not the same. So these are time variants. These are like, you have some moody friends, right? One day you go and make a joke to him, and he laughs and becomes very happy. The following day you make the same joke, he just says, he just gives you hell. So this is called time varying people, right? Their mood, their response changes by time. So we do not like those kind of people, and we do not like those kind of systems. We are very happy with linear time invariant system. So what is linear system? I didn't define that yet, okay? Time invariance, and the last thing I will talk about is linearity. This is the most beautiful property you have. So let's say you have a system, you have an input, you have output, right? So this is like vector spaces, if you remember from linear algebra course. For u1, for input, for u1, input, output. Let's say output is y1. For u2, the output is y2. Okay? Two different experiments. You take this system, you take u1, you inputted it, and you see the output is y1. You take another input, u2, separately, okay? u2, and you observe the output is y2. Now you do the third experiment. For alpha u1 plus beta u2, the response should be alpha y1 plus beta y2 for all u's and alpha and beta. Okay? Then such a system is called a linear system. Of course, would this mean, for example, that if the input is 0, the output is 0? It does, right? If you pick alpha and beta 0, then output is 0, right? It's called corollary. So such systems are called linear systems. If they are on top of it time invariant, we are even happier, okay? And this course will be all about linear time invariant systems. And as a matter of fact, you could say that 90% of electronics engineering is about linear time invariant systems. Because everything else, we approximate it with linear time invariant system because we don't know what else to do. Because we know linear time invariant systems in and out. And every day we discover more and more. So we are able to design, analyze, stabilize. We do marvelous things. All this is technology you see around you based on these things. Of course, there is that 10%. Also, that's very important. Okay? So I will see you next class here. Okay?